Hi everyone, this is Mrs. GA, and today we're going to be learning about the law of sines. So just a few facts about triangles that I want us to remember. When we are labeling a triangle, angle A is always opposite side A, angle B is always opposite side B, etc. So you can match the sides and the angles with the same letters, but the angle is always going to be uppercase, the side is always going to be lowercase. I also want you to remember the relationships between the angles and the sides. So the largest angle is always going to be opposite the longest side, and the smallest angle is always opposite the shortest side, and that works in either direction. So we are going to be using this statement later on to help us figure out a couple problems. All right, so the law of sine states that in triangle ABC, you can set up these following ratios where the sine of angle A over side A equals the sine of angle B over side C, or the sine of angle C over side C. And of course, you could do the reciprocal of all three of these ratios and it would still work. So we use law of sines for the following scenarios. When we know an angle, a side, and an angle, and we can use law of sines to help us finish solving for the triangle. When we have the side and the angle, or when we have side, then angle. However, we are going to be careful with this one because we might get one solution, we might get two solutions, or we might get no solution. All right, let's look at case 1, which says in triangle ABC, angle B is 57 degrees, angle C is 60 degrees, and side A is 15. So we are going to solve the triangle. So here it's really helpful just to draw a picture of what's going on. And again, it really doesn't matter where you put A, B, or C, and let's note that this is definitely not drawn to scale. So we're saying that angle B is 57, angle C is 60 degrees, and side A, which would be this side, is 15. So you'll see this is an angle, side, angle scenario, which means we can use law of sines. So you'll notice here that we can quickly find angle A using the triangle sum theorem. So we know that angle A should be 63 degrees. And now we can set up our ratio. So I'm always going to look for one ratio where I know both the angle and the opposite side. And that's going to be a starting point for us. And then we can use law of sines to either find side B first or side C. So let's say we want to find side B first. I'll label this side B. So I'm going to set up the ratio like this. B over the sine of 57 equals 15 over the sine of 63 degrees. The reason why I did it in this way is because I know I'm solving for this, so I'd like it to be in the numerator if possible. Just make sure your ratios match side over angle, side over angle. And now we can multiply both sides by sine of 57. And then this is what you would plug into your calculator. And we would get approximately 14.1. And then we can do the same thing to solve for side C. So here we could say C over the sine of 60 equals 15 over the sine of 63 degrees. Multiply both sides by the sine of 60 degrees, which we should know is root 3 over 2. And let's get a decimal approximation. And here we get approximately 14.6. And now we have found all of the missing parts of our triangle. All right, go ahead and pause the video and see if you can find all of the missing parts of triangle ABC. All right, let's go ahead and check our answers. So here you see that I drew a little triangle just to help me visualize what's going on. Here I set up A over sine 30 equals 100 over sine 110 to get A equals 53.2. And b over sine 40 equals 100 over sine 110. B is approximately 68.4. Okay, so now let's look at another case. Here we'll have a different set of information, but we can still solve it using law of sines. So here, again, I'm going to draw a little triangle to help us visualize. Nothing is drawn to scale. Please keep that in mind. So angle A is 20 degrees. Angle C is 25 degrees, and side C is 80.4. So here we're going to find the rest of the information in the triangle. The first thing we can find pretty easily is angle B, which should be 135. And here you can see we can use law of sines because I know an opposite side and an angle. So I can use this as a ratio. So let's start by finding side B. So we can say B over the sine of 135, which is root 2 over 2, equals 80.4 over the sine of 25. So notice side length over angle, side length over angle. So in my calculator, I will plug in 80.4 times the sine of 135 degrees all over the sine of 25. And B is approximately 134.5. Now we can do the same to find side A. We can say A over the sine of 20 degrees equals 80.4 over the sine of 25 degrees. So let's multiply both sides by the sine of 20. And if you plug this into your calculator, you get approximately 65.1. And there you have it. So again, a slightly different set of information because here you have an angle, and then a non-included side, but you can still use law of sines just as easily. All right, go ahead and pause the video and give this one a try. See if you can find all of the missing parts of triangle ABC. All right, let's go ahead and check our answers below. So here's my picture. You can see that we have an opposite side and an angle, so we can use law of sines. We can really easily find angle B using the triangle sum theorem, and then we just set up these two ratios to find A and B. All right, so before we do that last case where we know a side-side angle, I want to talk a little bit about arcsine and a couple important things to know. First, we use arcsine when we have an equation and we are solving for the angle. So we can use this inverse function to help us find theta. However, it's really important to know that the range of arcsine is negative pi over 2 to pi over 2, which is the same as, of course, negative 90 degrees to 90 degrees. So you may be wondering, well, why do we care about the range of arcsine? And the reason why is because of this restricted range, your calculator, whenever you're using arcsine, will only give you an answer between negative 90 and positive 90. So you might also be thinking, okay, so what? That should be fine. Well, what if we have something like this? The sine of theta equals positive 1/2. If you plug this into your calculator, if you type in arcsine of 1/2, your calculator will tell you 30 degrees. But we know that there's actually another angle whose sine is positive 1/2, and that would occur in quadrant 2. So we know that another answer would be 150 degrees. However, again, your calculator will only tell you this answer because technically, again, arcsine, the range of arcsine is only between negative 90 and 90. So just be aware that your calculator can only tell you answers in quadrant 1 when there may be an answer in quadrant 2 that also works. All right, so keeping in mind what we just talked about, let's try this last case. So we actually will have 3 examples for this side-side angle case. So here, again, I'm going to draw a quick triangle just to help us visualize, not drawn to scale. Here we're told that angle A is 45 degrees, side A is 7 root 2, and side B is 7. So we know that we can use law of sines because we have a pair of angle and opposite sides. And so if I do another pair, that means that we are going to be solving for angle B. But before we actually start solving, I'm going to see if we can figure out something about angle B using the relationships between the angles and sides. So if you compare the lengths of these 2 sides, what you'll notice is that, well, 7 is less than 7 root 2. Well, that means that angle B must be less than angle A, because remember, the shortest side is always opposite the smallest angle. So I know if this side is longer, this angle must be bigger. So the other thing we can conclude, since angle A is 45 degrees and angle B is smaller than it, we know that angle B must be acute. Okay, so if angle B is acute, that means that when we are using our calculator and we're going to use arcsine, the answer that we get will be in quadrant 1, and that will be our only answer. There's no way that angle B can be obtuse. There's no way that angle B can be in quadrant 2, because again, we know that angle B must be smaller than angle A due to the lengths of their opposite sides. So we can set up a single equation and we can expect to get a single solution. So we can say sine of B over 7 equals the sine of 45 degrees, which is root 2 over 2, over 7 root 2. And let's isolate sine of B. So 7 times the sine of 45 degrees over 7 root 2. And now we could say B is the arc sine of 7 sine of 45 degrees over 7 root 2. And remember, just like we talked about in the last slide, your calculator can only give you a single answer that will be in quadrant 1. In this case, that's okay because we know that angle B must be acute. So we'll plug this into our calculator. And we actually get that B is 30 degrees exactly. Now again, since we know that angle B must be acute, we know that we will only have one solution for this problem. So I know that this is the only possibility for angle B, which means that I can now find angle C. So using the triangle sum theorem, we know that 45 plus 30 plus angle C must be 180, so angle C is 105 degrees. And then once we know what angle C is, we can use law of sines again to help us find side C. So we can say here, C over the sine of 105 degrees equals 7 root 2 over the sine of 45 degrees. So if you solve for side C, you get approximately 13.5. And now we are done solving. Okay, let's look at another side-side angle case. So in this one we have, let me draw a quick triangle. Angle A is 43.1 degrees. We know that side A is 186.2 and side B is 248.2. So again, we have a side angle case. Since I have a pair of angle and opposite side, I know that I can use law of sines. So I see that I would be finding angle B first. So again, let's see if we can figure out something about angle B before we start solving. So in this case, we see that 248.2 is greater than 186.2. Okay, that means that angle B, the opposite side, is larger than angle A, the opposite side of this, or the opposite angle of this. So since angle B is greater than angle A, here, that means angle B could be acute or obtuse. So this is a case where we may have two triangles, or of course we may get no solution depending on the numbers. So any time that you look at this and you are not positive that angle B is acute, this is when you can expect to have multiple solutions. So let's see if we can find one of the solutions and then we'll find the other. So I'm going to set up my equation. I'll say sine of B over 248.2 equals the sine of 43.1 degrees over 186.2. So that means that B is going to be the arc sine of 248.2 times the sine of 43.1 degrees all over 186.2. And then this we can plug into our calculator to get approximately 65.8 degrees. Okay, so now this is one possible solution but remember, when you plug this into your calculator can only give you an answer that's between -90 and +90. So this is one answer, but then let's see if we can find the other value of B. So essentially, again, what your calculator just told you was this angle B. But again, it cannot give you an answer that is larger than 90 due to the restricted range of arc sine. So we know that there's actually another angle in quadrant 2 that has the same value. So we're actually going to use B as our reference angle to find the other value for B. So we're actually going to do 180 minus 65.8 to give us the other possibility for angle B, which is 114.2 degrees. Now, these two different angle B's give us two different triangles. So let's finish solving for this angle B. So we're assuming if this is angle B, then angle C would have to be 71.1 degrees. And then we can set up a ratio to find side C. So C over the sine of 71.1 degrees equals 186.2 over the sine of 43.1. And that would give us a side length of approximately 257.8. Now, if I use this other angle for angle B and I do my triangle sum theorem, my other angle C would have to be 22.7. So remember, I use angle B, angle A, which was given, and this would be my new angle C. So now I have a different value for side C. So C over the sine of 22.7 degrees equals 186.2 over the sine of 43.1. So if you plug this into a calculator, you get approximately 105.2. So again, just to recap how we knew that this was a two-solution problem, when we looked at the possibilities for angle B, we know that angle B is larger than angle A due to the inequality of their given opposite sides. So that means that angle B could be acute, because there are angles that are larger than 43.1 that are still acute, but it also could be obtuse. So your calculator can only give you the acute answer. So we got 65.8. And then we know that there's also a possible answer in quadrant 2. So we actually use 65.8 as a reference angle to find that other angle. So those are 2 possibilities for angle B, which gave us 2 different possibilities for angle C, which gave us 2 different possibilities for side C. But it's important to note that these all go together and these all go together. They would be 2 completely different triangles. All right, let's try one more together. So here again, let's draw a sketch to see what's going on with our given information. So here we're told that angle A is 42 degrees, side A is 70, and side B is 122. So again, this tells me that I can use law of sines. This tells me that I will be solving for angle B. So let's see what we know about angle B. Since 122 is larger than 70, we know that angle B is going to be larger than angle A. Again, since angle A is 42, that means that angle B may be acute or obtuse. So this tells us that we should definitely be on the lookout for a potential 2 solution case. But we also might get no solution, as you'll see in this problem. So let's set it up. The sine of B over 122 equals the sine of 42 degrees over 70. So here, B is going to equal the arc sine of 122 times the sine of 42 degrees all over 70. And if you plug this into your calculator, you get domain error. The reason for that is that this value, if you plug this into your calculator, this value is slightly larger than 1, and it turns out that the domain of arcsine is also restricted. It's between -1 and +1, so this is something that is not possible. So if you ever see domain error, that means that this triangle actually has no solution, and then we're done with this problem. All right, so at this point, I'm going to ask you to pause the video and give these 2 problems a try. Remember, be on the lookout for a potential 2 solution case, in which case you should find all of the missing parts for both triangles. Okay, let's check our answers. So for part A, I know that since angle B must be larger than angle A, I might get an acute angle or I might get an obtuse angle. So this is a case where you're going to look out for 2 potential answers. So you set up your ratios and you solve for B using arcsine. Your calculator will tell you 52.0 degrees, and your calculator is physically not able to tell you the other answers. So you have to know to expect it, and you say, okay, I know there's another angle in quadrant 2 that will have the same answer, so we use 52 as a reference angle, and we can find our obtuse answer, which is 128 degrees. So if you have 52 degrees, that gives you this for angle C and this for side C. If you have 128 degrees for angle B, gives you this for angle C and this for side C. So again, anytime angle B might be acute or obtuse, you could get 2 answers, or like in example B, you might get no answer. So again, I see that angle B must be larger than A. I set up my triangle or my ratio and I solve. My calculator tells me domain error because this value is actually larger than 1. So this triangle has no solution. And there you have it. All right, last thing we're going to do is try a couple of word problems that may involve law of sines to help us solve. So this says airplane A is flying due north. So just a quick reminder, north, south, east, west. So here's airplane A. Airplane A is flying due north towards the airport, which is 20 miles away. The pilot notices airplane B 45 degrees to her right. So if you draw an angle that is 45 degrees going to the right, somewhere over here we'll find plane B. Now this next piece of information is a new type of measurement for us. This is a way to show navigation. This says airplane B is flying north 40 degrees west. So when you see something like this, it means start at due north. So I'm going to draw in a due north line. This is just a guideline to help us. And this means from north, you go 40 degrees towards the west. So that means that it would go like this. And actually, this angle is 40 degrees. So again, from due north, we go 40 degrees towards the west. So this angle is 40 degrees, not this angle. It's really important to note that. So based on the information, how far is airplane B from the airport? So we want to find this length. So we are going to need to start with something from geometry. If you remember, you have two parallel lines cut by a transversal. These angles, since they are alternate interior, will be congruent. So this angle is also 40 degrees, which means that this angle in here is 85 degrees. So obviously this picture is not drawn to scale. So now we should have enough information to use law of sines and to help us find this, the distance from airplane B to the airport. So let's set up our equation. So here we can say x over the sine of 45 degrees equals 20 over the sine of 85 degrees. So x is going to be 20 times the sine of 45 degrees over the sine of 85 degrees, which is approximately 14.2 miles. And there you have it. So here, this is kind of that new navigation that I want to make sure you're comfortable with. So again, this tells us to start at due north and go 40 degrees from that line towards the west. So a little bit different than normal unit circle measurements. All right, and here we're going to try one more problem together. So this says flights 104 and 217 are both approaching SFO from directions directly opposite one another, and both are at an altitude of 2.5 miles. So that's how high they are in the air. So that means, so maybe here's SFO, and it says they're both approaching SFO from directly different directions. So one's coming from this direction like this, and one's coming from this direction. And both, again, are 2.5 miles in the air. So it says the pilot on flight 104, let's call this flight 104. I'll put it inside the airplane, and that means this is flight 217. The pilot from flight 104 reports an angle of depression of 17.8 degrees. So remember, anytime you have an angle of depression, it needs to be drawn from a horizontal. So we do need to draw on that horizontal, and this angle is 17.8 degrees. And the pilot from flight 217 reports an angle of depression. Again, it needs to be touching a horizontal of 12.7 degrees. What is the distance between the planes? So they would like us to find this distance. So we could start by using triangle sum theorem to find this angle. So it'd be 149.5 degrees. So I see that I have part of a setup for law of sines, but if I need to use either of these angles, that means I need to know one of these two side lengths. So we can actually just temporarily look at just this right triangle that's created, because we know that in a right triangle we can use sine, cosine, or tangent to help us find missing sides. So here I know that this angle is 72.2 because these two angles are complementary. It makes a 90-degree angle. So if I want to find this side length, I'll call this y. And using my given information, I can create the equation. I can say cosine of 72.2 degrees equals 2.5 over y. adjacent over hypotenuse. So y is going to be 2.5 divided by the cosine of 72.2, which is approximately 8.2 if we round. So now that I know this length, I can now use law of sines for my larger triangle. So we can say x over the sine of 149.5 equals y, which is 8.2, over the sine of its opposite angle, 12.7. So x is going to be 8.2 times the sine of 149.5 degrees divided by the sine of 12.7 degrees, which is approximately 18.8 miles. So again, with this problem, just be careful when you're drawing your angle of depressions. That's a really common mistake that I see, is that maybe we would call this the angle of depression. And then just remember, sometimes we will need to go back to our basic SOHCAHTOAs anytime you see a right triangle to help us find a piece that then we can use for law of sines. All right, that's all for today's video. Thank you so much for watching.